Welcome back to Cellular Signals, where we delve deep into the intricate tapestry of life sciences. Prepare for a journey back in time to the very origins of complex life. My name is Ryan, and today we will be talking about a passion of mine, the mitochondria. Today's episode will navigate the deep waters of mitochondrial origins, their mysterious bond with eukaryotic cells, and the persistent hints that suggest they might still be treated as foreigners within our cells. Eukaryotes, the form of complex life that is you and me, animals, fungi, and plants, developed at least 2.7 billion years ago. Already 1 to 1.5 billion years of prokaryotic evolution had come before. The event that resulted into the formation of eukaryotes was potentially unique, and a moment in time which may be a major limiter if complex life can form elsewhere. Picture a world dominated by simple, single-celled organisms. Among them were the proto-eukaryotes, the ancestors of modern eukaryotic cells. Unlike their simpler bacterial counterparts, these cells had a nucleus and other specialized structures, marking a significant leap in cellular complexity. However, their energy production capacity was limited and wouldn't facilitate more complex arrangements beyond a single-celled existence. Imagine a primordial scene where an ancient proto-eukaryotic cell engulfs another, an ɑ-proteobacterium. This chance encounter wasn't just a meal, it became a partnership, one that would shape life as we know it. The widely accepted model proposes that the origin of mitochondria came from a eukaryote swallowing a crummy ɑ-proteobacterium. However, this union wasn't always harmonious. In the beginning, two separate entities tried to coexist in one shared space. Each had its own goals and interests, creating a clash within the cell. Remember, the ɑ-proteobacterium didn't just willingly give up its independence. Both its energy-making skills and its genetic blueprint took time to integrate fully into the host's framework. As the engulfed ɑ-proteobacterium settled into its new environment, it faced a profound existential challenge. On one hand, its natural instinct was to reproduce and grow, thus potentially increasing its numbers within the host cell. This biogenesis, unchecked, could overwhelm the host, taking up valuable resources and potentially endangering the very environment the ɑ-proteobacterium now called home. But the host cell had a mechanism to restore balance, an early form of selective autophagy known as xenophagy. By selectively degrading and consuming some of the proliferating ɑ-proteobacteriums, the host could ensure that these internal guests didn't overstay their welcome. This process was a fine-tuned dance, a mutual understanding that evolved over time, as xenophagy in full force would have eradicated the ɑ-proteobacterium, and likely did for hundreds of millions of years or more. Why this delicate balance occurred is a mystery, and perhaps another reason to thank the error-prone nature of DNA. To put this into context, it would be like having a roommate who suddenly invites their entire extended family to stay indefinitely. The living space becomes cramped, resources are stretched thin, and tension brews. Imagine if there was a system where, if the family became too large, some would decide to leave, ensuring harmony in the shared space. This balance was not just about coexistence, it was about mutual benefit. The host cell gained enhanced energy production capabilities from the ɑ-proteobacterium, while the ɑ-proteobacterium got a protected environment rich in resources. The interplay between ɑ-proteobacterium, biogenesis, and xenophagy wasn't just a temporary truce, it was the beginning of an evolutionary partnership, setting the stage for the complete integration of the ɑ-proteobacterium into the host cell, eventually leading to the birth of the mitochondria as we know them. I have mentioned a few different cellular processes so far, one of which is autophagy. Just to give a brief overview, although I think this should be an episode in itself, Autophagy might sound complex, but let's break it down. Derived from the Greek words auto, meaning self, and phagy, meaning eating, autophagy essentially translates to self-eating. But this isn't some cellular horror story. Instead, autophagy is a sophisticated and vital process that ensures the health and survival of our cells. At its core, autophagy is a recycling program. Imagine your cell as a bustling city. Over time, buildings, proteins and organelles get old, machinery breaks down, and waste accumulates. What do you do with the debris? You can't just let it pile up, blocking the roads and alleys. Instead, you deploy cleanup crews to dismantle the outdated structures and reuse the materials to build anew. That's essentially what autophagy does. When nutrients are scarce or certain cellular components are damaged, autophagy ramps up. It engulfs the damaged or unnecessary cellular material within double-membraned vesicles called autophagosomes. These vesicles then merge with lysosomes, where enzymes break down the contents, providing the cell with fresh resources and building blocks. It's a beautifully orchestrated process, ensuring that waste is not just eliminated, but recycled. Now, while the basic concept of autophagy is a broad cleanup operation, there's a more targeted version of this process, selective autophagy. Just as the name suggests, this mechanism is more discerning. Consider our city analogy once more. While a general cleanup crew might tackle various tasks, sometimes you need specialists. Perhaps a particular building is deemed hazardous and requires immediate attention. Instead of waiting for the general crew, you'd send in a specialized team to handle that specific problem. Similarly, selective autophagy identifies and targets particular cellular structures for degradation, be it damaged mitochondria, mitophagy, invading pathogens, xenophagy, or specific proteins. Selective autophagy ensures that particular threats or waste products are swiftly dealt with. Both autophagy and its selective counterpart play crucial roles in cellular health, defending against diseases and facilitating cellular adaptation to various stresses. As we unravel more about these processes, we come to appreciate the incredible precision and efficiency embedded within our cells. My own research looked to establish the balance between the mitochondria and the autophagy machinery. To get back to our main story, xenophagy isn't just an ancient process. It's a cellular defense mechanism against foreign invaders like pathogens. Intriguingly, there's a parallel between xenophagy, which targets external threats, and mitophagy, which maintains mitochondrial health. Humans have built-in systems that protect against pathogens using machinery like ATG5 and ATG16L1. Yet, some pathogens can bypass these defenses, making certain individuals more susceptible to infections, highlighting the importance of autophagy machinery beyond quality control. It's astonishing how these two processes, xenophagy and mitophagy, share common elements. Both can function without ubiquitin, a cellular tag often used for protein degradation. Also, proteins like TBK1 play dual roles in pathogen detection and in mitochondrial quality control. As we trace back the origins of mitochondria and their integration into eukaryotic cells, an intriguing aspect emerges. Despite the intimate relationship that's been fostered over billions of years, there remains an enduring sense of foreignness between our cells and these critical hubs of metabolism. This isn't just a philosophical or evolutionary sentiment. There's compelling cellular evidence pointing to it. Mitochondria, once autonomous entities with their distinct genetic material, have come a long way. While most of their genes have migrated to the nuclear genome of the host cell, they've retained a small portion of their DNA, termed mitochondrial DNA or mtDNA. This mtDNA serves as a beacon, reminding us of their ancient, free-living past. It's fascinating how our cells respond to misplaced mtDNA. Picture a tight security system that's always on alert for foreign invaders. When mtDNA finds itself outside the confines of the mitochondria, it triggers cellular alarms akin to detecting an external pathogen. The sea geese sting pathway, a cellular defense mechanism, activates a potent inflammatory response. Why this dramatic reaction? It's likely an evolutionary safeguard. While nuclear DNA, which resides in the cell's nucleus, has its protection mechanisms, like the barrier to auto-integration factor 1, BAF, mtDNA doesn't share this privilege. Its presence outside the mitochondria is perceived as a potential threat, and the cell responds accordingly. This sensitivity to misplaced mtDNA suggests a profound evolutionary echo. Though mitochondria have been part of eukaryotic cells for over 1 billion years, the cellular machinery might still remember their separate origins. This perception of mitochondria's semi-foreign nature could have its roots in the ancient checks and balances set up by the host cell and the engulfed ɑ-proteobacterium. The relationship between a cell and its mitochondria is like an old, intricate dance. The steps and rhythms might have evolved, but the essence remains. While we've come to rely on mitochondria for energy production, metabolism, and even cell death, certain cellular systems may still treat them with a hint of caution reminiscent of their original autonomous nature. The mitochondrial saga, from a once independent organism to a critical cell component, is a testament to nature's ingenuity. But the traces of their distinct origins, like the whispers of an ancient language, still echo in the complex interplay between mitochondria and their host cells. It's a testament to the beauty of evolution and how ancient partnerships continue to influence life. Thank you for joining us on this evolutionary journey with cellular signals. A bit of trivia for you: the logo for this podcast is of a mitochondrial network being trimmed by mitophagy, with autophagosomes being formed at the tips. Hope you can see that. Tune in next time as we continue to unravel life's most intricate tales, because I must remember, each cell carries stories waiting to be unveiled.